Alright, so with the first question I actually wanted to take it our way. It was to actually just run through the idea of balancing equation with you. So the first reaction here, which is reaction 3, is a very popular famous reaction. But let's break down the equation first. It doesn't look like your usual one because you have this very interesting arrow. So this is called the double-headed arrow, and it's to represent reversible reaction, and you will officially be able to learn this only in year 11. But what that basically means, this arrow means, is that reactant can actually become product, and the product can at the same time turn back to the reactant, so it goes both forward and backward. So this is what we meant by reversible reaction. And this particular reaction here is the famous one. It's known as the Haber process, because we actually end up making the pungent gas ammonia, which is really, really, really important in the making of fertilizer. Okay, so with that, we're going to try to balance. I know I just block out the numbers in front for the coefficient in the beginning, but hopefully you didn't see it. So we're going to run through the idea of balancing here. Okay, so split that reaction into left and right. We want to make sure the left and the right balance out. So the first thing I want to look at is one element at a time. We look at nitrogen. So nitrogen, nitrogen, I'm going to split it. Okay, on the left I've got 2, but on the right I only have 1 right now, so I'll put a 2 in front of NH3, so I end up with 2 nitrogen. Again, there's a multiplication effect. Okay, coefficient multiply with whatever's behind it. Okay, then the next element I'm going to look at is hydrogen. I've got H2, 2 on the left, and right now I've got 6 hydrogen on the right, because 2 multiplied by 3 would end up with 6. So how do I make sure the number of hydrogen on the left equals to 6? I'll have to put a coefficient of 3. So if I multiply 2 by 3, I'll also end up with 6. So that's how we usually balance out the Haber process equation. Okay, I want to add a little bit of, I want to use reaction 6 and ask you to find out what's the percentage of nitrogen in this compound. Okay, so how do I go about doing this? So what I'll do is I will use 14. I'll find the MR first. Okay, MR of this substance is 14 plus 4, because every hydrogen has a mass of 1. Then I've got my second nitrogen, plus I've got 3 oxygen. I'll end up with 80. Okay, so the percentage of nitrogen in this substance, in NH4NO3, is I need to find out how many nitrogen are there. There are 2, and 2 nitrogen has a mass of 28, because every hydrogen is 14, isn't it? So I use the mass of both nitrogen over 80, and I multiply by 100%, and I'll end up with 35%. So what this 35% means that in ammonium nitrate, which is NH4NO3, 35% of this compound consists of nitrogen. Okay, alright, then we move on to the part E. Part E is, okay, we've got some data. We've got this mass of ammonia. Whenever you're given kg, turn it into grams immediately. Okay, the reason being because MR or AR refers to gram per mole of a substance. Okay, so we should keep the unit consistent, so it's always going to be in gram, and we need to use reaction 6, which is this reaction here, to solve this question. Okay, so basically what this means here, if I were to rewrite the whole thing, NH3 plus HNO3 equals to NH4NO3. I've got this mass of ammonia. I want to find out the mass of ammonium nitrate. Okay, so the first thing first, always get that triangle ready: mass, mole, AR or MR. And if you have been following my first set of video, you will know that AR, MR is always from the periodic table. Okay, learning how to use the periodic table is an essential skill set that you must have. So the first thing here is I want to find the mole of whatever information that's given to me, which is ammonia. mole equals to mass divided by mR. So my mass I've already converted into grams. My mR, would be 17. How do I get 17? Because every nitrogen is 14, every hydrogen is 1. Okay, you end up with 2000 moles, and then you do mole ratio. Mole ratio of what you already know, which is ammonia, versus what you want to find out, which is ammonium nitrate. So if you use the balance equation, you will see that I'm going to try this. There's actually no number right in front of it, right? And what this means is the ratio of all of them is 1:1:1. That means from the balance equation, if you have 1 mole of ammonia, you will produce 1 mole of ammonium nitrate. So that means if I've got 2000 mole of ammonia, I will actually produce 2000 mole of ammonium nitrate. Okay, so the third and final step is they want to find mass, right? Mass of ammonium nitrate, and that would be equals to, if you use the triangle, mass is right at the top, so you're using mole multiplied by the mR. Mole would be 2000, and mR we calculated it just now over here, it's 80. You end up with this in gram, or you could convert it to kg. So regardless of what your answer is, if you want to put kg, then your unit will be this. If you want to put it in gram, then it'll be like this. Okay, so 3 marks in your pocket. Alright, empirical formula. Favorite question, can't go wrong, right? And the steps are always the same. So let's just commit some time to practice and you should get it. So you list out all the elements. Then the first step here is to either use mass or percentage. So the mass is this, in percentage. Titanium is this, oxygen is this. Second step, use the periodic table to find the AR. Iron is 56, titanium should be 48. Let me just do a quick check. Yay, it's 48. Okay, and oxygen is 16. Okay, so do the same thing for 36.8 divided by 50. So my third step here, really ugly, let me try again. My third step here is to find the number of mole. Again, mole equals to mass divided by AR or MR. So to find mole, I use step 1 divided by step 2. So I'll end up with 0.657 for this, 0.658 for this, 31.6 divided by 16, and 1.975. Fourth step, okay, divide by smallest number. And what do we mean by that? Is you compare this tree and you try to identify among this tree which is the smallest. You will see that, hey, these two, they are actually the smallest. They are very similar. So everybody divide by this, the smallest value, and you end up very nicely with 1, almost 1, and then 3. So what this means is the empirical formula for this compound is Fe1, but 1 in chemistry is not required. Ti1 again, but again you don't need to write a 1, and O3. And you have proof yourself to be worthy of 3 marks. Okay, moving on. Okay, catalyst. Okay, catalyst here, it's what we have here. Okay, so we have this. This is a very popular reaction in redox. Okay, but what we have here is hydrogen peroxide solution. It breaks down to form water and oxygen gas. If I were to ask you to add in state symbol for this, what will you write? So it's nicely balanced, you just need to add in state symbol. Can you see the clue here is solution? Whenever you see the word solution, the state symbol will be AQ. That means state symbol for H2O2 is AQ, water is always L, unless they say it's steam. Then your H2O, the state symbol will be G. Okay, and oxygen is a gas, so it's G. Okay, this question here is more of a practical based question. They are asking you what should be kept the same to ensure this basically to ensure that this experiment is fair. Okay, so the first thing you need to make sure is the concentration of H2O2 solution is the same, right? And the second is the volume of H2O2 solution. Okay, for example, if you are doing like 2 rounds of solution, two rounds of this experiment, you can't be having like the first round 1 mole per dm cube. That's basically the concentration, and then the second round you increase the concentration to 2 mole per dm cube, right? Or like in the case of volume, first round you use 100 cm cube, but second round you drop it to 10 cm cube. How is it fair? How can you make a comparison like that? Okay, so to ensure that the experiment is fair, you need to make sure your constant variable remains the same. So in this case, these are your constant variable. Okay, next thing here is on catalysts, right? Okay, so maybe before we look into the idea of catalyst first, we break down the definition of catalyst. Catalyst has a it's defined as a substance, okay? A substance that increases rate of reaction. I'm just going to shortcut things by providing an alternative pathway with lower activation energy. Okay, what this means is, say for example, my y-axis is my energy. Okay, I start off with this energy for reactant and I want to convert it into a product. Without a catalyst, this probably is the activation energy, and the activation energy refers to the initial energy, A, initial energy required for the reaction to kickstart. Okay, however, if I have a catalyst, my activation energy can be significantly lowered such that it takes a shorter amount of time to convert it into a product. That's the beauty of catalyst. And not only that, not only can it speed up the rate of reaction, it actually remain chemically unchanged. That means you can still collect it at the end of the day and then reuse it, because it's not being used up in that process of a reaction. It's just there to speed up the reaction only. It basically provides a surface area for the reactant to come together, to bind together at a faster rate that allows them to convert directly into a product. Okay, so if you were to look at the question here says, which solid does not seem to act as a catalyst? The answer is quite obviously B, because there's no oxygen collected. So for this kind of questions, you're using the data which is provided in a table to answer your question. Okay, so it's like 1 mark each only. So part B, which is the most effective as catalyst here would be the one that significantly reduce the amount of time to produce the result that you want. So in this case, we're looking at the time, the shortest duration of time, and it's very clear it's going to be D. Okay, because it only took 11 seconds to collect 100 cm cube of oxygen, right? Okay, so that's that, and then we look at C. We are asking add 1 gram of solid A. Okay, how do we know that from the experiment that A was a catalyst, not reactant? Describe. So you need to explain a little bit more, kind of like writing a story, isn't it? Okay, so the first thing you need to do is, if I were to look at the setup is like that. Okay, so imagine you have your solid A in here. We've got 1 gram of solid A. So what you want to do here is first thing you want to do is to filter. And if you need a quick recap what filter looks like, filtration looks like this. You've got your filter funnel and your filter paper. And what you're trying to do here is you're trying to capture solid A. Okay, because it's a solid, it will it will remain on the filter paper. Okay, so you want to filter and you want to dry and weigh solid A. Okay, so whatever is on the filter paper you want to weigh out. And what exactly are you trying to see here? You want to see that the mass actually remain unchanged, or you can say, since the question say they give you 1 gram, you could say that the mass remain the same at 1 gram. So this proves that it's a catalyst, because a catalyst is not used up during the practical. Okay, it remain chemically unchanged for the entire process. Okay, this one. We've got neodymium as a metal used here. Okay, so give you information. Every statement is an information. Okay, don't just skim through the entire question and just dive into balance equation. So understand that neodymium is a metal. I probably think that's how it's been pronounced. If I got it wrong, sorry about that. And we want to balance this equation. Okay, so first thing. Okay, so I'm going to go one element at a time. ND, 1 on each side. Okay, that's fine. Then we go to fluorine, which is 3 on the left hand side. And on the right hand side, we have got only 2. Oops, supposed to be highlighted. Only 2. So what's going to happen here is I'm going to put a 3 here. So my fluorine is going to have 6 on the right. And now I only have so I put a 2 here. Okay, so what I have is, by putting a 2 here, I will also end up with 6 fluorine on the left, and this 2 also affected my number of ND. Right, so I'm going to put a 2 there as well. Wait, let me rewrite it. Okay, and my number of calcium, which I'm going to use this, would actually be 3. That means I would also have to put 3 in front of my calcium on the left hand side. So that's how I balance my equation. Okay, next question here is going to be on a little bit of like chapter 1 on kinetic particle theory. So we are saying the reaction mixture is 1100 degrees Celsius. So just imagine this container now is 1100 degrees Celsius. They are asking you which 2 substances are still solid. So this question needs you to go back to this table and give you the idea of melting point. So melting point is the temperature at which a solid turns into a liquid. So if my container now is 1100 degrees Celsius, what substance will still remain as solid would be this solids would have the melting point above 1100 degrees Celsius. So in this case, it will be calcium fluoride and neodymium fluoride, okay, would be still remaining as solid. Okay, just writing here. Alright, part 3 was most likely the type of bonding. Okay, so if you're in year 10, by year 10 you will have been introduced to 3 types of bonding: ionic, covalent, and metallic. Okay, so based on my first statement, do you still remember this? The starting statement here is this element neodymium is a metal. So we have got a metal and we've got a fluoride, which is a non-metal. So in the case of a metal, what a metal would do when it's in the presence of a non-metal is it's going to give away its valence electron. And in this case, the metal will become a positive ion and the non-metal will become a negative ion. So when we have positive and negative ion, essentially the type of bonding in here will be ionic bonding. Okay? Alright, let's move on a little bit. Suggest the formula of this. Okay, formula. Okay, there we go. So the only clue you have for this is here. Okay, I'm just going to highlight this. You can use red. I'm going to bring this here. I've got a formula of NDF3. Okay, so what does it mean to have this formula? I'm sure you already know by now that fluoride, because it's in group 7, has a negative charge of minus. Okay, and there are 3 of them. Then what does it mean to for Nd. What is the charge of Nd? So the overall charge over at fluoride is 3 minus. That means my Nd should have an overall charge of 3 plus, isn't it? So that's how we work backwards to identify the charge of this ion. So we're going to write this ion here, Nd 3 plus, and oxide, because it's group 6, oxygen ion is group 6, so it's 2 minus. For those of you who prefer the crisscross, we're just going to crisscross the number, right? And we're going to make sure we crisscross all the way to the bottom, crisscross all the way to the bottom. Your final formula will be Nd2O3. And what this basically means, for those of you who are more visual in learning, Nd3 plus, there are two sets of this, okay, and for your oxide, there are 3 sets of oxide. Okay, why is it like that? Because if you were to add up, if you were to add up the charge of the positive ion, you actually have a total charge here of 6 plus. And if you were to add up the charge of the negative ion, it would be 6 minus. So the overall charge for this ionic compound is still going to be 0, and therefore the formula will be Nd2O3. Okay, hopefully this helps. If you have still a little bit of question here, feel free to drop me a message on Instagram. I'm more active there. don't leave a comment on YouTube, just for me to park resources only. All right, one last question on metal reactivity. Thank you for being with me so far. For this question, it will be best for you to write down the metal reactivity series. And yes, you need to remember this by heart. I have my way of remembering things like this, okay? And it's really lame, but it works for me. It works since I was 15 years old. Now I'm 50, so you know the number of years I've remembered this. Okay, so metal reactivity, start with this. Pop star can make all zombie, and be like, what are you talking about, Miss Ang? Right, so K, as you can hear just now, is pop star, right? Because it reminds me of potassium. I'm using the words to help me remember the first alphabet of the metal. Okay, make. Okay, so it's pop star can make all zombie. In, which is iron. Tau, which is Sn. Tau, tin. It's hardly used these days. In tau, loose, which is lead. His, cool. And then Singapore, Sg. Sg because it's silver and gold. Okay, there's a reason why I put the H. I put the H in a bracket, because H is technically our non-metal. And what happened here, it shows that the metals under H, they are unreactive metal. They are not reactive with, they will not react with acids. Okay, so this series is supposed, as the name suggests, is reactivity. So the higher they are, the more reactive the metal. The lower they are, the more unreactive these metals are. If you think about it, if you have gold jewelry, you see that the gold jewelry can still maintain its shine and luster, even if you wear it for a long period of time, right? Yeah. So, okay, let's go back to the question. The question says that we have got 4 metals, and we've got one metal here that we do not know its identity. We want to add strip of zinc into the solution of each metal. So how this looks like is, just imagine I'm adding zinc into all of them. And you'll see that some reactions have no change, right? And we'll find out why. Okay. Oh, there we go. See part B? They asked for this. See why there's no change in the experiment with zinc nitrate solution. So if we take a look at this first, we are adding zinc into zinc nitrate. Why is there no change? It's because it's the same type of metal, isn't it? So zinc cannot displace itself. Okay, and then we have part A. In the substance that caused the brown coating on zinc, the brown coating is here. So we're technically looking at the second reaction, if I were to write down this reaction in words, in chemical formula, so zinc plus copper nitrate, I just want to take a moment to emphasize this, okay? Zinc ion, this formula you have to remember, because while you can find zinc in the periodic table, you can't find a group number above zinc. So there's no way you can know what's the charge of the ion immediately, okay? And then nitrate is also one of the polyatomic ion. So polyatomic ions, please get familiar. They are not found in the periodic table. I'm just going to write down the formula here. Hydroxide, nitrate. Okay, these two are the negative one. We've only got one of them that's a positive charge, ammonia. And then our sulfate and our carbonate, they are the 2 minus ion. Okay? Remember? Okay, so back to my equation. Sorry to digress. Okay, what happened here is I would actually form, because okay, my zinc, I'm trying to compare my zinc, try to put zinc into a copper nitrate solution. And let's take a moment to appreciate the metal reactivity series, okay? So we have got zinc here and my copper is over here. Now the more reactive metal is on the top. So what this means is my zinc is actually more reactive than my copper. Therefore zinc has the ability to displace, can displace copper from I would say from copper nitrate solution. Okay, so what we see here technically is our zinc being added to copper nitrate, and because zinc is more reactive than copper, what we have here is we form zinc nitrate, so the copper has been kicked out. Okay, so what we see here, the brown coating is actually copper being formed. Copper formed on zinc. Okay, because again, it is back to the metal reactivity series. So what else? What other observation can you notice from here? If you remember your qualitative analysis, copper ion solutions are actually blue. So this solution is actually blue to start with, but because at the end of the day, there is no more copper ion, so the solution will actually turn from blue to colorless. So this is one observation, and the second observation is because copper is being formed, we actually get brown coating on zinc. I'll try to find you this practical video via YouTube so you can visually see the change in the solution color as well as this brown color coating on zinc. Okay, I hope this helps. Let me know if this is helpful. I would love to create a little bit more of this kind of resources for you. Alright, see you around. Bye.